This video describes motion at constant acceleration, and in particular goes through the derivation of a couple of equations for motion at constant acceleration. So start with a quick description of constant acceleration, and then the equation derivation and an example. So the main example we use or we refer to for constant acceleration is the acceleration due to gravity. We remember that as an object falls in a straight line towards the Earth's surface, it's accelerated by an acceleration equal to 9.8 meters per second squared in the downward direction. This is an example of constant acceleration because, as we've discussed, that acceleration is always there. It's always downward, and it has the same magnitude. It does actually change relative to how close you are to the Earth's surface or to the center of the Earth. And so the acceleration at very high places is actually a little bit lower. But for our cases, the acceleration is constant. Other examples are things like pressing down on the accelerator of your car. We can often approximate situations where that's constant acceleration, but there are very few examples where it really is a constant acceleration. Typically, the acceleration changes for various reasons. So we saw with an object falling, like the baseball in the picture on the right, that the plot at constant acceleration has a parabolic shape for the position and a linear relationship for the change in position with time, which is the same as the velocity. Examples of this constant acceleration, we can now focus on this lower set of equations and graphs. We will derive these equations today, and the graphs, we looked at something similar except for an object falling downwards, or for a negative acceleration, we looked at similar kinds of graphs where we found that the position is always parabolic, whether it's a upward curve or a downward curvature. The velocity is a straight line, and this could be a positive slope or a negative slope. And the acceleration is either positive or negative, but the acceleration graph will always be a straight line for constant acceleration. So the kinds of questions that we can answer after this is what happens when we drop a coin from something high, like the Leaning Tower of Pisa, knowing particular parameters. This is very common examples and surprisingly useful. Things like how long will it take? We'll get into more examples as we go. So a note, if you have a note card, this is a good time to start building our equation note card. We'll talk about this in class and also distribute note cards if you don't have them. So when we're dealing with constant acceleration, we see a plot here on the right. Velocity versus time is a straight line. And we can write the definition for the x component, because we're dealing in one dimension, of average acceleration as change in velocity divided by change in time. In other words, the slope of this line. So the average acceleration in the x direction is delta v sub x delta t, and that's equal to vx final minus vx initial over t final minus t initial. And this will remind us of the definition of the average velocity, which was v sub x average equals delta x delta t, x final minus x initial over t final minus t initial. All right, so we've got that definition of average acceleration. We're going to use that in a couple of different ways. We can rewrite this as by multiplying both sides by t final minus t initial, and then discover that the final velocity will be equal to v sub x initial plus a delta t, where instead of writing t final minus t initial, we now have delta t. We're going to do this again in another way. So let's forge ahead. This is a fun derivation. We talked last time about how we can see that the displacement of the area under, the displacement delta x in some time interval delta t can actually be given by the area under the velocity versus time curve. In the case of constant acceleration, the velocity versus time curve is a straight line. So we can write the displacement, delta x, as the area under this curve. I've broken this into two segments. The first segment is this triangle, the top part, where the triangle, the equation of the area of a triangle, is 1/2 base times height. And here we have 1/2 base, which is t final minus t initial, times height, which is v final minus v initial. All right, so that part is the area of our triangle. And then we want to add the area of this rectangle underneath. And that is simply base times height. So the base is again t final minus t initial, and the height is v sub x initial, this value here, the initial velocity that we'd be dealing with. So we're going to use the result we had before and derive the position, the final position of the object. On the previous slide, we rewrote a sub x times t final minus t initial equals v x final minus vx initial. So let's substitute that in to the expression above. And so here's where it appears. We're substituting for the change in velocity right here. We've kept the rest the same. And we're going to now, instead of lugging around t final minus t initial, we'll just write that as delta t. So we've now got our delta x, same as x final minus x initial, is equal to 1/2 a times two terms of the t final minus t initial, which is our delta t squared. So this term times this term gives us delta t squared, plus v initial times delta t. And so given that this is x final minus x initial, we can now write x of t, which is the same thing as x final at any time, equals x initial plus v initial in the x direction times delta t, or t, plus 1/2 a sub x delta t, or t squared. We write delta t often to make it really clear, but when we say t, we're also talking about the change in time from some initial time. In this case, the initial time would be t equals 0. Okay, so this is the most complete equation we can deal with because it is an equation of motion. Equation of motion is x of t. It describes the position of the object at any time, and we can learn anything. We can, for example, figure out the object's final velocity, and if we simply take the derivative of that expression, we get v sub x I plus a times t, because when we take the derivative, we've got a 2 times 1/2, which gives us 1. So we've once again discovered that the final velocity, v at any time t, is equal to v sub x plus a t. Let's do a simple example. Let's say we drop a tennis ball from a height of 2.5 meters. How long does it take to reach the ground? So the first thing we do is draw a motion diagram where we've got our initial position, our initial time is 0, our initial velocity is 0, and we know the downward acceleration is equal to minus g. We're going to introduce this term for g being the acceleration due to gravity. And then we want to figure out the final time and the final velocity. So the most complete place to start is this. The final position is equal to the initial position plus vxt plus 1/2 a t squared. When we substitute in the values we have in our picture, in our motion diagram, we have 0 for the initial position, 0 for the initial velocity, and 1/2, the acceleration is minus g times t squared. So we then solve for t. T is equal to the square root of 2 times x of t. We actually already did this x final minus x initial part, divided by minus g. And plugging in values for this, we have our final position, it's not minus 20, this is a different diagram, is minus 2.5 meters. Our acceleration is minus g, which is minus 9.81 meters per second squared. And working that out, we get a value of 0.714 seconds. We'll think about how hard it is to measure precisely a time like that. It's less than a second. What if we wanted to know the velocity of the object just before it reaches the ground? We again have our motion diagram to refer to, and we remember that our final velocity equals the initial velocity plus a times t, which in terms of the acceleration and the initial values we know, a is equal to minus g. And so our final velocity is minus 9.81 meters per second squared times the time we just found, 0.714 seconds, and that's equal to minus 7.00 meters per second. Right, so that's one simple example. We'll do more examples like this in class and continue with our constant velocity work.